Imagine walking onto a factory floor, right?
Okay, I'm there.
And you've just poured hundreds of thousands of dollars from your startup's budget into this massive, custom-machined block of steel.
Oh boy. A big investment.
Exactly. You hit the start button, and then you just watch helplessly as the machine spits out thousands of perfectly defective plastic parts, like every single minute.
Yeah, that is a financial nightmare scenario.
It really is. And the crazy thing is, it happens all the time. And it's usually because of one hidden foundational variable, which is your mold choice.
Right. Because usually when we talk about manufacturing a product, there's this expectation of simple replication.
Like a photocopier or something.
Exactly. You have a master design, you load your raw material, you hit a button, and out comes an exact duplicate.
Yeah, it feels automatic. You hold a plastic toothbrush or a medical device, and it just feels like a totally solved problem.
But then you actually step into the real world of plastic injection molding, and that photocopier metaphor just completely shatters.
Totally. We're looking at a manufacturing landscape that is actually incredibly fragile.
It is.
So if you are a budding manufacturer, maybe you're looking to launch a new line of household items or automotive components or whatever consumer electronics, this deep dive is built specifically for you.
We've got a great source today, too.
We do. We're using this comprehensive guide from First Mold, authored by James Lai, as our roadmap today. And the mission here is providing mold selection advice for budding manufacturers and really evaluating production scale and risk.
Which is so critical.
Right. We are tackling the most important decision you'll face, which is choosing between a single cavity mold and a multi-cavity mold.
And, at a glance, that sounds like a really minor technical detail, right?
Yeah, like something you just hand off to the engineering team and forget about.
Exactly. But make no mistake, this is a massive strategic choice. It dictates your capital expenditure, your operating costs, your scalability, and really importantly, your ultimate exposure to risk. Jumping straight to high-volume output without truly understanding the physics happening inside that tooling. I mean, that can bankrupt a startup.
Okay, let's unpack this. We need to start with the basic mechanics. So a single cavity mold means you have one impression of your part cut into the steel.
Right. One cavity.
Yeah, one injection cycle produces exactly one part, whereas a multi-cavity mold has multiple identical impressions in one base. So one cycle produces 4 or 8 or maybe even 64 identical parts simultaneously.
It sounds so incredibly simple on paper. More cavities equal more parts.
Right. But the ripple effects are staggering. And before we even look at the engineering, we have to look at your wallet.
Oh, absolutely. The unit economics.
Yeah, the unit economics.
Well, the primary driver of this entire decision is production volume forecasting. With a single cavity mold, your initial tooling costs are relatively low.
So your CapEx risk, your capital expenditure risk, is pretty manageable.
Exactly. But your unit cost, the actual cost to make each individual plastic part, is high because that machine time, the labor of the operator, the massive amount of energy to melt the plastic, all of that is being amortized over just one single part per cycle.
To make this relatable, I kind of think of it like deciding whether to buy a single muffin from a bakery every morning.
Okay, I like where this is going.
Right, versus buying a massive state-of-the-art industrial oven to bake 50 muffins at once.
Right.
That industrial oven costs an absolute fortune up front. But eventually, if you run it constantly, the cost to bake each individual muffin drops down to like fractions of a penny.
Yeah, but, and this is a huge but, for any budding manufacturer, that only works if you actually have enough customers lined up every single day to eat 50 muffins.
Exactly. If you don't have the volume, you just wasted all that money on the oven.
That analogy perfectly captures the financial tension. Single cavity molds are your safety net. They're ideal for prototyping or low volume production.
Or when your market demand is highly uncertain, right?
Exactly. They let you test the waters. You can make design changes without throwing away a massive initial investment.
Makes total sense.
But multi-cavity molds, those are your scale-up strategy. But to push your industrial oven analogy just a bit further,
Well, please do.
you also have to understand the limits of the kitchen you're putting that oven into.
Meaning the injection molding machine itself.
Precisely. You cannot just buy a 64-cavity mold and slap it onto any piece of equipment. You have to establish your machine capability constraints first.
Okay, what kind of constraints are we talking about?
Well, the number of parts you can make at once is strictly governed by things like shot size, injection pressure capacity, plasticizing rate, and clamp tonnage.
Hold on, let's break those terms down for someone who hasn't spent 10 years on a factory floor.
No.
What do those actually mean in practice? Like, start with clamp tonnage.
Sure. So when you inject molten plastic into a mold, you are doing it under extreme pressure. And the plastic wants to push the two halves of the steel mold apart. Clamp tonnage is the raw physical force the machine applies to keep that mold smashed shut.
Ah, okay. So if you have a massive multi-cavity mold with a huge surface area and your machine doesn't have enough clamp tonnage,
The mold gets forced open slightly by the pressure of the plastic,
even just a tiny bit.
even a fraction of a millimeter. And when that happens, the molten plastic seeps out of the cavities and into the seams of the mold.
Oh, wow. That sounds bad.
It is. You get what's called flash, these sharp, paper-thin edges of excess plastic on your final part. It ruins the dimension and requires manual trimming.
Yikes. Okay, and what about the plasticizing rate? You mentioned that one too.
Yeah, that is literally how fast the machine's internal screw can melt solid plastic pellets into a liquid state.
Hey, it's a speed limit.
Exactly. If your massive multi-cavity mold requires more liquid plastic per cycle than your machine can actually melt in that time frame, you are physically bottlenecked.
Okay, so assuming a budding manufacturer has the capital and they have a machine big enough to handle the tonnage and the melting rate.
Right, assuming all that is in place.
It is so tempting to just look at a spreadsheet, cross your fingers on your volume forecast, and choose multi-cavity from day one for those beautiful unit economics.
Oh, incredibly tempting.
But I want to push back on this a little bit. Why is the multi-cavity mold itself so expensive to build?
Yeah.
Like if you have a CAD file, a computer design of a plastic part, and you just need a CNC machine to cut that exact same shape into a block of metal 4 times instead of 1 time, isn't that essentially just copy and paste? Why does the cost and complexity explode?
Yeah, that copy and paste assumption traps so many novice manufacturers.
Really?
Oh yeah, the complexity scales exponentially because of a principle called flow balance.
Flow balance. Okay, explain that.
Think of molten plastic, like a surge of rushing water trying to fill a complex network of tiny pipes in a fraction of a second.
Okay, I'm picturing it.
With a single cavity design, you have one pipe, one direction of polymer flow, one point where the plastic enters, and a predictable way to cool it down.
Which is why you can make what they call steel-safe adjustments, right?
Exactly.
Like if the single part isn't perfectly sized, you can take the mold out, polish a tiny bit of steel away, and try again without worrying about ruining anything else.
Precisely. But the moment you move to a multi-cavity design, you are no longer optimizing a single component. You require systems-level engineering.
Systems level, because of all the different pipes.
Yes. If the design of the runners, which are the channels delivering the liquid plastic to each cavity, if they aren't perfectly mathematically symmetrical, the flow dynamics will betray you.
Betray you how?
Well, if the plastic reaches one cavity just a millisecond faster or at a slightly different pressure than another, you end up with a short shot in cavity A.
Meaning the plastic solidifies before filling the shape.
Exactly. While cavity B gets way too much pressure and produces that flash we talked about earlier.
So you just go in and widen the runner for cavity A so it fills faster, right? Problem solved.
Ah, if only. If you try to make a corrective change to fix the short shot in cavity A by widening that runner, you instantly alter the pressure and flow balance of the entire mold.
Oh, because the plastic takes the path of least resistance.
Exactly. You might fix cavity A but simultaneously starve cavities B, C, and D. It's a completely intricate web. And we haven't even touched on cooling.
Let's touch on it. Why is cooling a plastic part so complicated? Like, don't you just let it sit there for a second?
If you just let it sit there, the heat dissipates unevenly. Plastic shrinks as it cools, you see.
Oh, right.
So if it cools unevenly, it warps or develops what we call sink marks, where the surface actually caves inward.
That doesn't sound like a good toothbrush.
Not at all. So to achieve absolute thermal uniformity across a multi-cavity network, engineers have to design highly complex internal cooling circuits.
What does that look like?
We're talking about baffles, bubblers, and even conformal cooling, where they use 3D printed water channels that snake around the exact three-dimensional contours of the cavities inside the solid steel.
That sounds incredibly expensive. And all of those cavities have to be identical down to the microscopic level, right?
Yes.
So tolerance stacking becomes a nightmare. If you have 16 cavity inserts, they require high-precision electrical discharge machining, or EDM.
Right, where they literally use electrical sparks to burn away steel at the micron level.
Wow.
Yeah. Because if the parting lines are misaligned by just a hair, the whole system fails.
Which brings up a really critical realization about the factory floor. The complexity of a multi-cavity mold doesn't just magically disappear once the metal is cut.
Not at all.
It simply morphs from a design risk into an operational risk.
Absolutely.
And here's where it gets really interesting, because a lot of founders think, great, the engineers figured it out, the mold is installed, the hard part is over.
Do you think it's smooth sailing?
Right. But how much downtime are we actually talking about if just one cavity out of, say, 32 starts acting up during a production run?
A staggering amount, honestly, if you aren't prepared.
Really?
Yeah. See, a single cavity mold has a wide processing window. It's forgiving. It can tolerate slight variations in the factory's ambient temperature or the machine's injection pressure.
And if there's a defect, troubleshooting is pretty linear and direct.
Exactly. But a multi-cavity mold requires massive ongoing maintenance. More cavity inserts, more gates, and more complex cooling circuits simply means significantly more points of microscopic wear and failure.
And from an operator's perspective, troubleshooting becomes highly ambiguous. I mean, the machine doesn't just pop up a little error screen saying, hey, cavity number 14 is broken.
I wish it did, but no. You might have one cavity producing sink marks, another flashing, and 30 running perfectly.
How do you even begin to figure out if it's a systemic machine imbalance or a localized fault in the steel?
You certainly can't guess. You have to rely on advanced diagnostics.
Like what?
Well, this means integrating cavity pressure sensors directly behind the steel walls to measure the exact force of the plastic in real time. It means using thermal imaging cameras to look for hot spots on the mold face. And often it requires conducting short-shot studies.
What does a short-shot study look like in practice?
An engineer will deliberately underfill the mold. They'll set the machine to inject only 50% of the required plastic, then maybe 60%, then 70%.
Oh, I see.
Yeah, by looking at these partially formed parts, they can physically see the wave front of the molten plastic. They can see exactly which cavities are filling faster than the others, and then trace the root cause of the imbalance.
But while you're conducting all these studies and tweaking sensors, the machine isn't running, you're bleeding money.
Every minute counts.
Or worse, you have to do what they call a cavity shutoff.
Oh yeah, that hurts.
You literally block off the bad cavity so the others can keep running. But if you block off 4 cavities in a 16-cavity mold...
Your incredible throughput numbers just plummeted by 25%.
Exactly. Your whole unit economics calculation is destroyed.
Which underscores why strict preventative maintenance is absolutely non-negotiable. You're constantly battling mechanical degradation.
Right.
Take ejector pin galling, for example.
Ejector pins are the metal rods that physically push the finished part out of the mold, right?
Exactly. And every cycle, you have metal rubbing against metal. Over hundreds of thousands of cycles, that friction creates microscopic shavings and wear.
Oh, man.
The pins start to stick or they leave these deep scratches on the plastic parts. It's just a constant, never-ending war against wear and tear.
So, to mitigate these operational risks, to squeeze out the maximum efficiency, manufacturers naturally turn to automation. They bring in the robots.
They do.
But your mold choice dictates the entire robotic ecosystem you have to build.
Absolutely. The whole goal of automation is improving overall equipment efficiency, or OEE. It's about reducing scrap, moving human operators to quality control rather than just monotonous extraction,
Right.
and tying the whole cell into SCADA and MES systems.
Okay, let's define those acronyms quickly for the listener.
Good call. SCADA stands for Supervisory Control and Data Acquisition. Think of it as the central nervous system of the machine, tracking the injection pressure and temperatures down to the millisecond.
Got it. And MES.
MES is the Manufacturing Execution System, which tracks the broader factory floor operations, like inventory and work orders. Automation feeds data into these systems constantly.
But let me play devil's advocate here for a second.
Go for it.
If I'm a small manufacturer trying to keep my capital expenditure down, why bother with robots initially? Even with a multi-cavity mold, shouldn't I just have a human operator open the door and pull the parts out by hand to save money?
Human intervention is actually incredibly risky for a multi-cavity process.
Really? Why?
It comes down to the thermal rhythm of the mold.
The thermal rhythm. That sounds almost musical.
It kind of is. Think of the mold as a giant breathing lung of heat. Plastic enters at, say, 400 degrees. The water lines cool it down, the part is removed, and the cycle repeats. That specific rhythm dictates the dimension of the final part. If a human operator takes just 2 seconds longer to extract the parts on one cycle because they were, distracted or adjusting their grip.
The massive block of steel cools down slightly more than it did on the previous cycle.
Exactly. And that tiny drop in temperature completely changes the fluid dynamics of the plastic on the very next shot, potentially ruining all the parts.
Wow, so the robot isn't just about saving on labor costs, it's about maintaining the physical thermodynamics of the steel.
Precisely. The robot provides absolute, unwavering consistency. It minimizes thermal variation and prevents the operator from accidentally scratching or contaminating the parts.
That makes total sense.
For high-speed multi-cavity cells, automation becomes almost mandatory. But as you hinted at, the robotic engineering required is vastly different.
Yeah, because single-cavity robotics are pretty simple. The end-of-arm tooling, the EOAT, is usually just a basic vacuum cup grabbing one part. The payload is super light.
Right.
But multi-cavity robotics require an EOAT with numerous perfectly aligned pick points.
Suddenly, your automation engineers have to manage the physical rigidity of the robotic arm. If you have an arm whipping into a machine to grab 32 parts, you have to calculate payload distribution.
You have to manage inertia.
Yes. When the arm stops moving, it naturally wants to vibrate. If you don't engineer vibration damping into the system, the arm shakes, the suction cups miss the cavities by a millimeter.
And the machine literally crushes the robot arm on the next cycle.
Exactly. It's catastrophic.
Yeah.
Furthermore, the programming has to coordinate staggered ejection behaviors and incredibly specific timing.
It's just an entirely different league of manufacturing.
It really is.
And speaking of different leagues, as we look at the absolute peak of scaling complexity, there is a specialized type of multi-cavity tool that throws every single rule we just discussed completely out the window.
Oh, the family mold.
Yes, the family mold.
The ultimate engineering challenge.
Seriously. So a family mold creates completely dissimilar but related parts in a single injection cycle.
Right.
Think of molding a large plastic housing and the tiny little retaining clips that go with it at the exact same time in the exact same tool.
It's wild.
On one hand, it sounds brilliant for inventory. You never have a surplus of housings without the matching clips.
From a supply chain perspective, it's elegant.
Mm-hmm.
But from a plastics engineering perspective, it borders on the impossible.
Because you're dealing with varying flow lengths.
Yes. Wildly different fill pressures and entirely different cooling and shrinkage rates across the different cavities, all happening simultaneously in the exact same block of steel.
Going back to our oven analogy earlier, this is literally like trying to bake a massive 20-pound turkey and a tiny, delicate cupcake in the exact same oven.
I love that.
Set to the exact same temperature for the exact same amount of time and trying to get them both perfectly cooked.
That is the perfect visualization.
Yeah.
It highlights the absolute necessity of holistic systems thinking. Because if your cupcake is burning, meaning the small retaining clip is getting too much pressure and flashing, and you try to fix it by simply lowering the machine's injection pressure.
Your turkey comes out raw.
Exactly. You get a massive short shot on the large housing. Fixing a defect on one component inherently jeopardizes the other. You cannot isolate variables.
It's all connected.
It is. You have to look at the pressure profiles as a single unified ecosystem, balancing the runner diameters, the cooling circuit performance, and the venting efficiency holistically. It requires the highest tier of engineering talent to execute successfully.
So what does this all mean for you, the budding manufacturer listening right now?
That's the big question.
Choosing between a single cavity and a multi-cavity mold is not just some footnote you leave to the end of a product design cycle. It is the DNA of your business model.
It really dictates everything that follows.
If you are starting out and your volume is uncertain, utilizing a single cavity mold protects your capital.
Yes.
It gives you a forgiving process window to learn the ropes of injection molding, stabilize your quality control, and really just test your market fit.
You only scale up to a multi-cavity mold, or heaven forbid, a family mold, when your forecasted volume definitively justifies the exponential increase in engineering costs.
And the automation requirements and the continuous operational maintenance.
Right. And, that leads me to a final sort of provocative thought regarding the future of manufacturing.
Lay it on us.
We see a massive push toward what they call lights-out manufacturing.
Automated cells running 247 with zero human intervention.
Exactly. But consider the gradual malfunctions we discussed earlier, like the microscopic wear from ejector pin galling that slowly, invisibly pulls a cavity out of tolerance.
Right, the silent killers of quality.
Yeah. If you remove the humans entirely, and you rely solely on the blind predictability of a robotic arm pulling parts from a complex multi-cavity mold,
Oh, I see where you're going.
how many thousands of perfectly defective parts might be picked, packed, and tracked by those robots in the dark before a human auditor finally realizes the steel is slowly degraded.
That is a terrifying thought for anyone managing a supply chain.
It really makes you think.
It's a stark reminder that no amount of flawless automation or incredibly expensive tooling replaces the need for proactive human vigilance.
And a deep understanding of the underlying physics. The machine executes, sure, but we must understand what it's executing.
We can't just hit copy and walk away. The stakes are simply too high. Well, thank you so much for joining us on this deep dive.
It was a pleasure.
And to you listening, whether you are actively building a manufacturing startup or you're just fascinated by the hidden complexity of the everyday objects around you, we encourage you to keep questioning the systems that build our world. Until next time.